Hello and welcome to our presentation. In this video we will be introducing you to the concepts that we've been studying in the module Curves and Surfaces. Essentially, we are given rigorous definitions to intuitive concepts such as the speed of a curve or how much a surface may bend.
As an example, we will be starting with this plane curve. A plane curve can be visualized as a bendy line that exists in 2D space. We first investigate whether a curve is regular. A curve is called regular if the speed of a function does not equal 0 in a given interval. The speed of a curve is given by differentiating the function. If a function is not regular, you can sometimes restrict the domain so that the function is regular. We can also work out if the function is unit speed. This means that the speed of the function always equals 1.
To check if the curve is regular, we differentiated the curve, which involved differentiating each coordinate in turn. This can be seen on the slide. Then, using trig identities, we simplified this to the following form. When t is equal to 0, the speed of the curve is 0. Therefore, we had to restrict the domain of t. We restricted t to lie between 0 and pi by 2, but it cannot equal either of them. By doing this, the speed will now never be 0. We then took the norm of the differential. This is not unit speed, as it does not always equal 1. We would then usually reparametrise this curve to make it unit speed. This process includes calculating the arc length function. To do this, we have to integrate the first differential, but this is a special integral that we know exists but cannot be calculated. On this occasion, we cannot reparametrise the curve.
The curvature can be defined by the amount a curve diverges from being straight. The curvature is denoted by the Greek letter kappa. The signed curvature indicates the direction of the bend, and this can be positive or negative depending on the given curve. The formula to calculate the curvature can be seen on the screen. It uses the differentials of the given curve gamma. You can also see the complicated looking formula on the screen, that is our curve's curvature.
We can now draw our curve using the curvature. In fact, by the fundamental theorem of plane curves, the curvature uniquely defines our curve up to rigid motion. Now we will look at a space curve, which is the same concept as a plane curve, except we include a third coordinate, and so the curve exists in three-dimensional space.
To find if the curve is regular, we again differentiated each of the coordinates in turn. This time we had to restrict the domain to 0 and pi to make the curve regular. Next, we worked out the speed of the curve, which is shown on the screen. We can see that it is not unit speed, as it does not always equal 1. Again, we could not make this a unit speed curve, as this would involve another integration which exists but is not known.
We calculated the curvature of our space curve using the formula on the slide. We first needed to calculate the second differential of the curve. Using this, we then calculated the cross product of this with the original first differential. This gives us a vector which is perpendicular to these two curves. The curvature is then the norm of this vector divided by the norm of the first differential cubed. I am now going to introduce torsion. This measures how much the tangent plane to the curve banks left and right. We use the formulas on the slide to calculate this. We had to calculate the third differential of the curve and the dot product between this and the previous cross product. The torsion is equal to 0.
You can obtain this space curve from the plane curve from before by setting the z-axis as 0. So when rotated, you can see all three coordinates. We're now going to move on and talk about surfaces. The picture and the equation you can see on the screen represent our surface. We needed our surface to be regular, and for a surface to be regular, there must not be any self-intersections. So we must set the domain as u squared plus v squared is less than 3 to achieve the surface you see on the screen.
We're ready to investigate some geometric properties of our surface. To do this, we calculate what is known as the first and second fundamental forms. The first fundamental form allows us to calculate areas and lengths over our surface, and it is given by these equations. So firstly, we partially differentiate our surface in both directions. The inner products of the partial derivatives in each direction give us the three coefficients of the first fundamental form. And, as you can see, that is exactly what we've done here. Now we'll be looking at the second fundamental form, For this, we need the notion of the Gauss map. The Gauss map is a function that gives us a normal to the surface at every point. The coefficients of the second fundamental form are found by taking the inner product of the Gauss map composed with x and the second partial derivatives.
The first and second fundamental form are used to compute the Gauss curvature, denoted by k, and the mean curvature, denoted by h. On the surface, in terms of the Gaussian curvature, in the middle it is more Gaussian curved, whereas on the edges it is less Gaussian curved. The mean curvature on our surface is constant, and in our example it is 0. When the mean curvature equals 0, this is what you call a minimal surface.
To understand these curvatures geometrically, we have to look at how these are related to curvatures of curves on the surface. If we say gamma is a curve on the surface, then the differential of gamma belongs to the tangent space of S at gamma of t. The inner product of gamma prime and the Gauss map composed with gamma is 0. If gamma is a unit speed curve, then these three are a moving frame of gamma. The second differential of gamma is given by this formula, where kappa n and kappa g are smooth functions. The curvature of gamma is given by the two functions through the second formula on the slide. If gamma is a unit speed curve, we can use these two formulae to calculate the normal and geodesic curvature. Since gamma is not unit speed, we cannot calculate the geodesic curvature. We can still work out the normal curvature using the formula on the slide. This gives us the equation given on the screen.
Having done some research around our curve and our curve's properties, we discovered a curve called Enneper's curve that is extremely similar to ours. You can see an animation of the self-intersecting curve on the screen. It is also a minimal surface, just like ours, which means that it locally minimises its area, just like a soap bubble.
This concludes our presentation. We hope that you've enjoyed this short meander into the field of curves and surfaces, and that we have awoken a geometric curiosity from within you. Goodbye and good luck.
Bye!